Electricity is produced by a number of means, and one of them is hydroelectric. The concept's actually not that difficult. What it is you build a reservoir, the water pours down through a pipe, and the weight of the water hitting a turbine spins the turbine, and that energy created is then converted into electrical energy, and that's how it works. Now, there's suddenly a lot of interest in generating from flows of water which don't have such a great height or such a great mass behind them. And under this bridge in Tokyo, there's a couple of hydroelectric generators that generate enough energy to light the bridge at night. And although the water drop is only 1 meter, it generates enough power. This has inspired a Japanese inventor to come up with a micro-turbine based on the Archimedes screw. The spiral blades are angled so that they rise up towards the upstream end, and a 15 centimeter plate blocks the upstream flow, and of course it builds up and runs over the top of the plate, flowing down through the spiral blades. That causes the generator to rotate, and the force of the water on the blades creates the electricity that then lights up a light. This idea goes anywhere there's a small amount of flowing water with a low drop. I love this idea and want to see if we can replicate it. The first step, of course, is to make the Archimedes screw.
The Archimedes screw was invented by Archimedes of Syracuse, apparently to pump water out of the hold of a ship. It's used for a ton of things. Like I say, auger bits are Archimedes screws, ground augers, grain lifts, just a huge amount of things, extraordinarily useful. And of late, it has been realised that they will operate in reverse if made from a helix, and they are making generators out of them, and the generators are in fact quite impressive. So I was asked to look at making an Archimedes screw. Unfortunately, the Archimedes screw as a helix is in fact quite difficult to make. That's the problem with it. There are a couple of parameters that are interesting. One is the pitch, which is the height between this and this. One section of this isn't called a screw or a thread, it's actually a flight. And then you have the external diameter and the internal diameter. So those are the parameters of the flights of an Archimedes screw helix. Now, there are flight calculators. You can actually just go on the net, put in Archimedes screw flight calculator, and it will calculate what you need the flat profile to look like. Because the standard methodology for this is to cut a flat profile out of some material and then stretch that profile out like you would a spring to make the actual flight. Then you put the flights on a pipe, that's exactly what I've done incidentally, and you make your screw. Now, the flights themselves are usually circular, very often made from plastic, very often made from metal. And I was looking around for something that would be really, really easy to get hold of and easy to use, and I came up with this: CDs. CDs are a polycarbonate, which means that when you heat them a little bit, they will get soft and you can distort them. That temperature actually is around about 140 degrees centigrade, something around about there. So we're working with an Archimedes screw, looking to make it out of these things, which are just old CDs. Now, these CDs do clean up relatively easily. DVDs, not so much, you have to split them apart. But these ones, the coating's on the top, so a trimming knife blade will scratch that off. And that's exactly what I did to a whole bunch of them. I scratched it off. But you'll notice I've also drilled out a rather larger hole, it's 48 millimeters actually, and put that cut in it down there so that it opens up. Now, something amazing has happened, even though it's just really tiny. All I've done is increase the size of the hole here from 15 millimeters to 40 millimeters. So in this flight, we've still got a fair amount of area, but suddenly it's got very much more flexible than it was before. So if I get a bit of ABS piping, and this is 40 millimeter diameter, and I stretch that out, actually it'll snugly fit against the piping. Now, that immediately made me think, and it should make anybody think, I think, what would happen if we tried joining that together? So, because it's now so much more flexible, I was able to heat weld this, and I'll give you an example of me heat welding it. And here's 5 of them heat welded together. And if I open them up, you'll notice it's opening up like a natural spring. Now, that's really kind of awesome, because we haven't had to muck around with this particularly. All we've done is heat weld those edges together, and then we can open it up like that. The idea, obviously, is, can we open it up so that all we have to do to create this thing is stretch that down a pipe. But let me give you a close-up of the heat welding process. So here's the disc, here's a block of wood. Take one end and slide it under the block of wood so that you've only got one side actually on, and that's the side that we're going to heat solder. Now we need to hold that flat, and I'm just using ordinary sellotape. We put a bit of sellotape on it, and then it holds that flat against there. Now we take another disc, and what we're going to do is hold that against there and heat weld those two. So we need to hold that flat. Again, bit of sellotape. Line it up carefully and sellotape it down. So the two are now butt joined. And if I pop a bit of wood under there, then I can actually get to that butt joint there. Now I've got a sacrificial piece where I'm going to use that as the soldering material, and here I've just got an ordinary soldering iron, and you just go along that line soldering some extra material on. And we need to do that to both sides. So what I did was stick a screw in the top and then pull the helix out along the pipe and then basically glue it in place. Now those joints are still pretty rough. Demon's 1988 suggested that I double up and then move it along so it laps, and I'll probably try that. It's getting a bit late, so it's probably going to be tomorrow. Now, I was planning on making the pipe work for the other helix that I did to try it as a hydro generator. But to be honest, I wanted to concentrate on the helix formation. And I think that's really getting there. Okay, so this is clearly turning into a bit of a mission. Now, I wanted to quickly test something, actually. So I've put a bearing at the bottom. I've got a little stick to hold it. Now, I've taken it out in the wind and it doesn't particularly turn in the wind. However, if I put a blower that blows up through these vanes, I mean, not earth-shattering as a wind turbine, but it is telling me that that pitch really is looking really good for a fluid flow across it. Now, obviously, the air was kind of angled here, catching the vane and making it spin a little bit. The idea of this is you put it in a pipe and you have the water flowing over it. Air is compressible, obviously, and this is going absolutely everywhere. We've got water with a bit of weight on that. We should be able to get that to generate quite well. Now, I have had a couple of goes at this, which is why you can see that the pipe is actually fairly scored, because I can tell you that sticks like you wouldn't believe. So the only thing that I'm worried about is the joints here. That's the thing I'm not really happy about, really. So I'll try Demon's 1988 suggestion, and we'll see what happens there. But at the moment, I think this is ready to put in the pipe with that suggestion. Now, I guess when you practice at anything, you're going to get better. So we're taking those CDs, cleaning them off, drilling a hole in the circle and cutting them into a C shape. And when we do that, we had a problem with the joints. The joints weren't pretty. I mean, they were strong enough, they just weren't pretty. And what I've done here is take up Demon's suggestion, lap them a little bit and epoxy glue them together. And now they're pretty. So there is 7 of them all linked together, making a really nice natural spring. So there's no heat treatment required. That actually spreads out on this 40mm pipe beautifully. So we've got this really nice Archimedes screw thing going on here, and that's going to be the basis of my water generator. Now you can see what I've done to that pipe. All I've done is put a couple of centered plugs in the end and then some aluminium rod to act as a spindle. So that's the spindle for my Archimedes screw. Now, of course, we've made that thing in its entirety, so we now need to find something to fit it in, or make something to fit it in. It's going to be a bit of a challenge, actually, to try and find a bit of pipe that's going to go in. So what we're going to do is we're going to make us around for it. Now, with water generators and Archimedes screws, they actually don't need to be enclosed totally. They can be open, there's no reason why not. If you're going to use them for a wind turbine, you would need them in a pipe, but you don't need them actually fully enclosed in a pipe if you're using it as an Archimedes screw. Now, I have seen Archimedes screw pipe generators where the screw has actually been fixed to the internal of the pipe, and the pipe has been allowed to rotate, and the takeoff has been from the pipe rather from a central spindle. I did like that, and there will be a time when I investigate that for sure, but right now what we're going to do is make a bit of enclosure for this. Now, we could make an enclosure, we could cover it in something, but of course we can't cover that in something because it'll just get stuck. So the first thing I've done is taken a whole load of paper, and I'm going to wrap that around my screw to make a pipe. Now, that paper is going to come out later. It's like a bit of cardboard really. Just make sure that we've got a pipe, and when we take it out of the thing that we're going to make, actually what we've got is a little bit of clearance as well, which is clearly quite essential. So we wrap around there, tighten it up, sellotape it down, and we automatically have a pipe. All we need to do now is make that more rigid. So to make that more rigid, I'm going to put a former on it. Now, the former I'm using here is what I call builder's board, but if you're in America you can get something called Sintra board, which is pretty much the same stuff. And if we put our spindle into there we go, close that up, all we need to do is cast something over that. Now, we're going to use this stuff. This is amazing stuff actually. It sticks to just about anything that you wouldn't believe, so it's going to stick to this Sintra board, no problem at all. Very lightweight and amazingly rigid, and all you have to do is spray it on as if it were icing a cake and then leave it for 2 hours. Now obviously if we spray it onto that paper it's going to stick to the paper, so we want something to stop it. What I've got here is a bit of polyethylene tetraphthalate, and I've put an angle on the bottom at 60. So that if I drop that angle in there and lay my pet over the paper, there we go, we get a nice U-shape. Now I've made it too long because it's a bit longer here because I didn't know how long that was. So what I'm going to do is trim that off and then put another piece of angle on, and when that other piece of angle is on and a spot of glue to hold everything square, we're ready to spray it with the foam. So I'm going to do that and get back to you, and we're going to spray it with the foam. Okay, that's it set up, ready to go. Now you might be wondering why one end is higher than the other, because obviously it's upside down at the moment. So when we turn it the right way up, that means we'll have a tilt in the flow of the channel. Okay, with this stuff, it's really easy to use actually, but it does take a tiny bit of practice, and you put it on as if you were icing a cake, something like that. Don't make it too thick because it does expand to twice its volume. And you finish that off. Now it's going to expand like crazy, but that's okay. You can always cut it off later because it just cuts and sands really easily. So I'm going to finish icing my cake, then leave it for a couple of hours, and then come back to it, it'll be done. Okay, so it's had a few hours to dry, and that's what it's looking like. Now it goes super rigid, but it dries with the permeation of air. So a big chunky bit like this needs a fair amount of time to dry. If you close it up completely, it'll never dry, so you need to leave a bit open. But you'll see I put sides on. So the last time we looked at it, it only had these two uprights. I put the sides on now and left this top to dry. So it's not quite dry yet. But we turn that over and pop it down. You can see because I did one leg longer and the other shorter, we now have a nice inclined plane where we haven't had to work out all the angles or worry about all that cutting. And sitting safely in here is our Archimedes screw in the central channel. So if I remove that paper now, we go. What we get is a perfectly formed channel with the Archimedes screw in it that's free to turn. Okay, there it is, finished. All I've actually done since we last looked at it is let it dry, and I've strapped a NEMA motor onto the spindle here to act as a kind of generator. A NEMA motor is what I've got, so if it generates something, that'll be awesome. It's got a rectification circuit on it and a couple of capacitors, so let's see if we can charge those capacitors. If we can charge those capacitors, we can light a light. Now, it is an energy scavenger. So it's done like this because I was watching a thing in Japan where a Japanese engineer had designed something that would use shallow, slow-running water to scavenge energy. And it's all over the place in Japan. They're putting it in drainage ditches to light lampposts. They're putting it in schools for emergency lighting. And I loved that idea. I mean, I generally love that idea anyway, since I think that scavenging energy is always a good idea. I mean, it's great to have the one big plant that will be your answer to all your ills. That's just awesome. But I also think it's important to pay attention to the scavenging possibility around you. Now, water's not something we use a lot of here in England, mostly because people don't have water streams on the whole in their land. Mostly here we have small plots of land without a ready source of water. But a scavenger like this, I would think you could put in a drainage pipe. And if you put it in a rainfall pipe, so you're collecting the rain on your roof, it goes in the downspout, you should be able to scavenge energy from rainfall, which would be particularly cool. So it's not meant to need a huge torrent of water to get it turning really, really quickly and generate a ton of power. It's not the point. The point is to scavenge energy from what is around. I mean, turbine screws, they are already using them. You find them in places where they're doing exactly that. Them large things with a big fall of water generating kilowatts of energy. You see that around. This is a scavenger, so it's meant to run small loads. Now, any generating device is going to perform better if you put a generator on that's actually matched to the generating device. Now, I've strapped on a NEMA motor because that's what I've got and I want to see it do something. Anyway, let's take it outside and give it a supply of water. Okay, so maybe chucking a couple of buckets of water in there doesn't give you definitive answers for everything you might want, but for me, that was an unqualified success. I'm really chuffed about that. I think it's really excellent. So the idea is you put it in a shallow stream. This is only 15 centimetres. It banks up, rushes down there, and hey presto, you've got yourself a generator. It's going to scavenge small amounts of electricity for sure. Now, improvements, well, one would be find a stream and stick it in there, obviously. But other improvements would be maybe putting in a double helix. That would work well. Obviously, matching the generator to the actual machine would be awesome. But I like it that we've been able to make this from basically scrap. I mean, it's made from CDs and expanding foam. So what we're going to do is take this little generator out to the stream and give it a go. So this is the little stream near where I live, and I've brought the Archimedes screw to stick it in the stream and see how it does. And there it is, churning away, and that's actually producing 5.1 volts, which, to be honest, is quite impressive when you think what it is. I mean, this stream's little more than an open drain, actually. And there's another shot of it. I built a little dam to the right-hand side as we're seeing it, and you can see it flipping around. It's great, 5.1 volts. So, I would say that was a success. Okay, personally I thought that was awesome, actually. The thing about something like this is it would be incredibly cheap to make. I mean, I made this out of builder's plastic, But you could just as easily injection mold it, vacuum mold it, blow mold it. But I'm figuring that the entire case would probably cost you, I don't know, a pound or two, something like that. So you could really easily make this entire thing for just a few dollars. And if you're in the right situation, then it could be an emergency power supply. It's certainly how the Japanese were looking at it when they were developing it. So it's an emergency power supply that is really, really cheap and does really well. Then I think that's an awesome thing, actually. What I'm really interested in is there a possibility this could actually be used for wave power? So we're going to take this down to the sea and give that a try. But before we do that, I just want to talk a little bit about some of what I think are the important aspects of this, mostly based on comments that have come up. Some things like, oh, you won't get much out of that, or no, you need a lot of torque, and all sorts of stuff that people have mentioned. So I wanted to talk about why I build these things the way I build them. Because to my mind, what determines the action of these things is not this bit. This bit on the end actually is a question of optimization to me. What's important is this bit here. This bit here is the bit that actually defines the amount of work this thing can do. This thing is a purely mechanical system. It's got a slope. It's going to have a weight at the top, which is the weight of water in this case. And that's going to roll down that slope with a known force. That amount of force is going to be the work that this can do at its maximum. So the maximum effect that this can possibly have is fixed by things like the properties of the material, the strength it has to carry that weight, the degree of slope that we've put in, how long it is, what volume it's occupying, just because that fixes the weight that's going to roll down that hill. I mean, this is, in concept, no different to having a rock on a hill. If I push a rock up to the top of a hill and roll it down, that rock will give out energy that's equal to the energy it took me to push it up there. And the advantage of this is I didn't have to push the water up there, and Mother Nature did it for me. She made it rain, that rain ran down in rivers, I stick this in a river, and all that work has been done by the environment, and I'm just collecting that work. I don't have to push the rock up the hill. But conceptually, a rock up a hill and this particular generator have no difference whatsoever. They're identical things. So this for me is the important bit of it, because this fixes the maximum amount of work that could possibly be done by this device just by its mechanical attributes and things like its volume, its slope, the speed at which I can get that stuff through there. All of that is what fixes the actual effect that this could possibly have. Well, why is that? Well, what it'll do is this bit here, which is the shaft, it'll turn that shaft with a certain amount of force. When you turn a shaft with a force, that's what torque is. Torque is the amount of force you need to apply to rotate something. So the torque on here is going to be fixed by the properties. So the amount of torque I can get is fixed by the mechanical device. The speed of rotation is also fixed by the amount I can throughput there, the rate at which I can throughput it. So the maximum amount of torque that I can get on that shaft and the speed of that shaft is all related to this bit here and has nothing to do with this bit here. This bit here is about converting that mechanical work into electrical energy. So it's got nothing to do with the amount of work that this can do. It's actually a question of efficiency. If I could use this to convert all of that mechanical work into electrical energy, it would be 100% efficient, and of course I can't do that. Even if I chose the best thing possible, I've still got elements in here where I'm going to get losses. So there's going to be less than 100% efficiency. The thing I stick on here is what's going to determine the efficiency of the machine, not the amount of power it can generate. And that's the thing that actually strikes me all the time. People talk about the whole thing as being it can only generate that much power, and that's actually just not right in my mind. In my mind, that is completely swapped over. They look at this first and almost ignore this. To me, I look at this first and then look at that as an optimization exercise as opposed to being core to what's going on. And I think it's just really a question of what you look at, really. It's how you view this thing. Now, power, actually, is going to be either strong and slow or fast and weak. Now that's really an interesting concept if you think about it. And it is something that defined the motorcycle industry in the sort of 50s, 60s, 70s. In Britain, based on our Victorian heritage, I mean, have you seen Victorian engineering? I mean, you get conrods as thick as your leg. And it was built that way because the material science wasn't that good, so they had to make things big to be strong. Now, of course, we've got great material science, and we don't need that anymore. We can make little things that are as strong as the great big things the Victorians were producing. So it's kind of a Victorian hang-up, actually. It's got to be slow, it's got to be strong. And that's the way the British industry made motorcycles for years, and they dominated the world market in motorcycles. And then the Japanese came along. And the Japanese get a bad press sometimes. I think they're an incredibly inventive people. And they said to themselves, hang on a sec. Instead of having a slow, lumpy engine thudding away, generating lots of torque to get power, why don't we have a light engine zipping around at Mach 10 on a short stroke and we'll get the same power? And of course that's exactly what happened. And because they were doing that with motorcycle engines, the motorcycles were as good as the British motorcycles, but a hell of a lot cheaper. And so they now dominate the world market in motorcycles because they saw that the damn thing didn't need to be lots of torque and slow. Now, if you're thinking about generation, and you're thinking about a generator, a wind generator, and you think, oh, that needs lots of torque. Well, it doesn't. What it is that those styles of wind generators are in fixed wind speeds where they turn slowly at the hub. They must turn slowly at the hub because they've got great big blades on them, and so at the tip of those blades they turn at massive speeds and they really stretch the materials. By the time you get to the hub, of course, you're looking at gear ratios, they're turning quite slow, but they need a lot of torque, and they need a lot of torque because they've got to turn a generator. They only need a lot of torque to turn a generator because they're turning so slowly. Now, what's in here is a bunch of wires and magnets. When we turn something quickly like that, the quicker we turn it, the higher the voltage. It's an application of Faraday's law. If we put a lot of wire in there and turn it through a magnetic field, we get a lot of current. That's just an application of Ampere's law. So we need them big and heavy if they're going to turn slow. So if they're going to turn slow, we need a lot of torque because the thing has to be big and heavy. If it can turn quickly and the thing is light, you don't need a lot of torque to get the thing to turn and to generate the power. Now, of course, there is another side to electrical energy generation. If I plug something directly into my generator, I'm adding to the power requirement because I'm basically putting a load on it, and it has to turn the generator and run that load, and that puts more work on that head, meaning that head has to have an even stronger torque. But we can dissociate that. We can dissociate that by sticking something like that in it. Well, this acts like is a sponge. It slowly fills up from the low torque, high spinning to fill it up. And then we draw our power from the capacitors. So the capacitors actually don't affect the generator because they have this bit as an interface between them, acting like a kind of sponge. So if you're going to use something like fast spinning with low torque, you need something in between that's going to disassociate the application load from the generator load. So if you look at it slightly differently, that you're not actually got a device that needs high torque, you've got a generator that needs high torque. You're looking at it, I think, the other way around. So if you've got a generator that needs high torque, well, you've got two options. Either change your generator for one that needs low torque and stick in a dissociation device, or create a device that generates high torque. So you don't need, I think, you don't need high torque at the shaft. I think that's an old way of looking at things based on Victorian principles. And I don't mean that to be an insult, so please don't take it that way. I think that what we need to look at when we're looking at these things is this bit, because this bit's the important bit. This bit obviously has a massive effect, but focusing on this means that you then don't look at alternatives here. Focusing on this means that you do look at alternatives here, and I think that's going to be a better thing. Now, because this is a slow-turning high-torque machine, the torque it can generate at that shaft is actually related more to the weight that you're going to put through it and the turning force on it. And that's going to be a relatively high torque. So this one's not like a wind generator. It's quite slow turning, it has quite high torque, and I've stuck this thing on it. And this thing is obviously a NEMA motor, and a NEMA motor is exactly what I was talking about. It's actually a low torque, fast spinning device. This is completely mismatched. I've got a high torque device attached to a low torque generator. I should have done it the other way around, but I don't have a fortune to spend on these things, so I tend to pick up what it is that I've got and give it a go. And the reason I do that is because I'm more interested in what this is going to do. What this is going to do is a different question. The linkage between the two is a question of optimization. So people, if you're focusing on this, you're focusing on the wrong thing, I think. You should be, according to my way of looking at things, focusing on this bit, because this bit is going to fix the amount of energy you can generate. Now that bit you can play around with to optimize the highest percentage. Okay, I feel like I've blabbed on enough. Let's go down the seaside and stick it in the sea. Okay, I thought that was awesome, actually. It's showing potential as being a wave generator. I mean, clearly I did this because I was looking at the Japanese stuff, and so I set it to what the Japanese inventor had actually done. I put it at that same angle, really, because I was thinking of the same things. So clearly the angle was wrong. There's clearly other things to think about. We didn't get much on that lapping, did we? I mean, we got like maybe a foot or so, something like that. So the active area was pretty much missed in this top section here. We got the action, sort of that bottom half section. So I've clearly made it far too long for that application, at the wrong angle for that application. And it makes me think as well that the blade diameter was far too small. What we need really is a bigger blade diameter so we can take more weight in that smaller movement. Because we're effectively, remember, rolling a rock up a hill. So we need a bigger rock, which means we need a bigger blade. But clearly, something like an Archimedes screw could be used for wave generation. I thought it was pretty exciting stuff, so I wanted to share it with you. Anyway, I hope you enjoyed the video, and thank you very much for watching.